Hi guys, I didn't create a video yesterday and I think I should have. We started our work on periodic motion, and periodic motion is any motion that just repeats. Okay, so that's pendulums, that's something bouncing up and down on a spring, and we can calculate it. So the first part of it was talking about springs and how you compress a spring and it wants to come back to normal. You can pull on a spring, put a weight on it, and pull that weight down a little bit more, and it'll start bouncing up and down. And that's really what your work was yesterday. And so I want to go ahead and talk about that example and why that example exists. There was a scientist, his name was John Hooke, and he was, sitting around like most scientists do. They go out and they say, oh, well, what do I want to play with today, and what do I want to think about today? And he decided he would talk about and go play with springs. So what he did is he created what is called Hooke's law. Excuse me. And Hooke's law simply states that the force applied to a spring is going to be equal to the spring constant times the amount of distance. So it takes in a certain amount of force to displace that spring or to compress that spring past its relaxation point. Okay, and this negative is a little confusing to a lot of us, because we think of negative as taking something away, and really it's just that restorative force that wanting to be back at its relaxed state. So it doesn't matter which direction we're going, that spring always wants to come back to being relaxed. And so we don't necessarily use the negative in our calculations. We just need to know that this is a value that doesn't add on to the force. Okay, and so we want to know that that's just how that spring wants to be restored. And so we don't figure it in our calculations. We talk about the example problem that was in your homework, and we talk about a bag of potatoes, and it had a weight in newtons of, I think it was 56 or 58, 56 newtons. And that was the amount of force that was being applied. That's the whole thing. And then with that weight of 56 newtons, the spring was displaced 18 centimeters, or 0.18 meters. And so you see in the example problem, it says, okay, well, if I know these two things, what's the spring constant? How badly does that spring want to get back to its relaxed state? And so we take this formula and we just have to solve for K. And so we say that K is equal to the force divided by the amount of displacement. And so it shows you in the text that if you take your 56 newtons and divide by your 0.18 meters, that you'll get a spring constant of about 310 newtons per meter. And that's a standard unit for spring force, right? You're going to have to apply 310 newtons of force to get that spring to move 1 meter away from its relaxed state. And so different springs have different spring constants. And then that was the first part. The second part of the problem was finding the potential energy within the spring. And this is where we had mentioned Hooke's law before, And I know some of us had talked about the potential energy within a spring, right? And the potential energy within a spring uses that same idea of Hooke's law. It says that the potential energy in a spring is equal to 1/2 the spring constant times the distance squared. And you could do all sorts of calculations and be figuring out, deriving new formulas from original formulas and get to this point. But suffice it to say, 1/2 kx squared gives us our potential energy of a spring. And so if we know how far we've pushed this spring, and we know its spring constant, we can find out how much energy is inside this spring, how much potential energy, and how fast it might move when we let go of it. And so we do a little bit of math. We found earlier that this was 310, and we knew that this was 0.18 meters, right? And we have a half. We're going to square our 18 centimeters. And if we do all that math, we really come up with about 5 joules of energy. I think it's 5.0 joules of energy. There's not a whole lot of energy stuck inside that spring because it's not really a big, hefty spring. 310 newtons to get that thing to stretch an entire meter, not a very hefty spring. But that's all there was to it, and that's what that example problem was trying to show us. And I hope you have a little bit better understanding of periodic motion. We're going to get into swinging pendulums, and we're going to get into waves and fun stuff like that shortly. But let's get this periodic motion idea down and have a great weekend, because we don't have any assignments. Your assignment, I think I stretched over a long period of time, maybe this assignment or another assignment. You don't have anything assigned to you tomorrow unless the one that I just assigned was extended. Have a great holiday weekend, and as always, stay safe. And I'll see you on the other side.